Hello, everybody attending online. Hello, the people here in the office. Today, in this the Inria talk of today, we have Geraldine Pichot. Welcome to, I don't know if to Chile, but at least to Inria Chile. Geraldine works in the Serena Inria project team. Her interests are around applied mathematics, high performance computing, and well, she's also looking at all these problems of the simulation of partial differential equations and these kind of things that for us actually it's very, very timely and interesting talk because we have a big overlap. We are interested also in the modeling of ocean flows and all of that. So today she's going to be presenting us the work around this topic of simulation of the environment, particularly the subsurface flow simulation. So thank you, Geraldine. Welcome. I'll let you the floor and we can start taking some questions and all of that. Okay. So one thing, the people attending online, please use the chat to enter your questions as they go. Okay.
Thank you so much for the introduction, and thank you so much for having me here. Thank you for the invitation. Thank you, Naya. Thank you, Julia, Astrid, and everyone here. I'm very happy to be here today and to present the team I'm in at Inria Paris, which is called Serena, Simulation for the Environment, Reliable and Efficient Numerical Algorithm. And I will also focus on most of what I'm doing at Serena, my work in the team. So here is the website of the team, if you want to have a look at it. We are 7 permanent members. The head of our team is Martin Voralik. So we have François Clément, Zaonan Dong, Michel Kern, and myself, we are Inria. Alexandre Ern is professor at ENPC, and we have also Jean-Charles Hilbert, which is also at Inria. And we shared in engineers, 2 engineers, Simon Legrand and Raphaël Zanella, with other teams. Our administrative assistant is Deria Gok, and we have currently 3 postdoc students, Diva, Eureka, and Stephen. And we have 8 PhD students, and including Daniel Tegara-Vasquez, who is my PhD student. And I will present most of the results I will present today is the results of his PhD. So, practical gallery, just to have an overview of what we are doing in the team. So it goes from computational mechanics, fracture networks is most of my things, wave propagation, also adaptive simulations. We would like to have the effort where it's really needed, where the solution needs to be accurate in some places. Multi-phase and reactive flow, and also CO2 sequestration. This is a benchmark that we have worked on, especially Michel Kent. And the applications are quite wide, going from waste disposal in the underground, like nuclear waste disposal, reactor operation, and also CO2 sequestration. And we have also industrial partners. So, so there is EFP, Énergie Nouvelle, EDF, Électricité de France, Andra, who is in charge of the nuclear waste disposal agency, CEA, Commissariat with Énergie Nouvelle, and Itasca, who is a company I'm working with, especially for the modeling of fractures. We are also developers. We build software to test the numerical methods and to make them available also to the community. So we have software implementing polytotal methods like H++, TemLab, which is MATLAB set of programs to deal with high-order finite element methods. We have also code about a posteriori error estimators. We have also François, who is working in COC. So we have also it's for proof, formal proof for numerical analysis. And the software I'm most working on is MODFRAC, which is a mesh generator, and NEF++, which is a suite of software for fracture simulation. Okay, regarding the theoretical gallery, so we are working, we try to work on, we work on polytotal meshes and schemes. We have experts in the team on like Alexandre and Martin, who are really So Alexander is one of the designer of HHO method. So then we apply this method to our applications. We have a posterior error control so that we can estimate the different components, error components in the simulation so that we can use them as a way to either refine the mesh where it's needed or to stop, for example, a solver at the right moment without so as to save computational time. And there are also works on space-time domain decompositions, adaptivity in linear and nonlinear solvers, and also, as I said, we have some people in the team working on mechanical proofs. Okay, so the loop in a nutshell. So we have models based on PDEs, numerical approximation methods, algebraic solvers, and implementation. And all of them, we want to have some reliability with some a posterior error control and also efficiency with respect to computational resources, and which we apply them to environmental problems. So here are some keywords of all the topics we are working on. So I will not go into the details, but so these are more the theoretical topics we are working on. So, and you can find more on the website as well through the publications with different collaborators. And we also have applications, sorry, so on wave propagation, flow in fractured fluid media, CO2 sequestration, and H2 storage simulation, and reactive transport. And today, I will rather focus on flow in fractured porous media. So this is mostly what I'm doing with colleagues in the team. A lot of people are working on this work with me, so I'm very grateful to them because I would not be here without them. I mean, it means a lot. We did all this work together, and some steps have been able to be done thanks to this collaborative effort. And so now I will go into the context and motivation of the work. So we are working on the subsurface flow. So we want to have a model of the subsurface. So as you can imagine, so you have here some examples. So the fractures are present at all scales in the subsurface. So you can have fractures from the meter scale to the kilometer scales, basically. So it's really important to take them into account because they really play a very important role in many physical and chemical phenomena. So they cannot be neglected. You have to take them into account in your simulation. And such simulations could be appear in different applications like energy or environmental application, going from oil and gas, water extraction, geothermal energy production, nuclear waste, and CO2 storage, and groundwater resources. And the challenging objective is to be able to perform realistic simulations and models of this underground. So we would like to do side-scale simulations, but how to do that in a cheap way, but accurate way? We would like to have some kind of radius models, but how to build radius model if you don't know the scales that matter the most in your simulation? So what we have done in the past years is to try to run accurate large-scale simulations so as to be able to perform, to produce radius models from this simulation, so it's very small scales. There are many challenges, as you can imagine. So we have a lot of uncertainty in the underground. There are missing scales. For example, you can have scales at the scale of the boreholes, which is centimeter scale. You can have outcrops, which is more like meter scale, or you have a map with kilometer scale, but you have a lot of missing scale in the middle. And then the first question is how to image a subsurface. You cannot dig into it, you will destroy it. So you have to find a way to model all these missing scales. It's a multi-scale model as well, because you have these small scales, small fractures, for example, and very big ones that you have to take into account in your model. So you need a generator of fracture network that is capable of representing the subsurface in a realistic way. And as I say, so we have a lot of uncertainty. So at some point, we would like to run a lot of simulation to be able to derive some upscale quantity, for example. So one simulation should be cheap, right? And this is the focus of our research, to make one simulation cheap. It's an heterogeneous media, like you have the water, for example, can flow through gravels in a few meters per hour, while in clay, it's less than 1 meter per 100 years. So you see the different scales in the flow that may appear. So this is not easy to take these different scales into account in the numerics. So this is something we have to be aware of, and taking special care about this heterogeneity. It's also an intricate geometry. If you look at the fracture network, for example, if you look at, for example, here, you imagine it's a rock and you see all the fractures on the top, and you can see the very, a lot of fractures, a lot of intersection between the fractures. The fractures are the black segments that you can see on the picture. And so we have generators. It's not our own generator, it's a LabCom factory, which is LabCom, Laboratoire Commun, it's in French, between CNRS, Itasca, and the University of Rennes, that have designed this kind of models to represent the fracture. But this is the one we are working with. And you can see that there are some similarities now with the representation of what they obtain with their simulators compared with what we observe in the nature. But of course, if you want to simulate flow, we use finite element method. So we need a mesh. And meshing the geometry, you can imagine it's not that simple, and so we need dedicated mesh generators. Next challenge, it's a 2D, 3D coupled problem. Why so? Because here you have fractures. So imagine you have this block, which is a rock, and all these colored ellipses inside are the fractures, which means the void in the rocks, right? And they are intersecting in an intricate way. You have flow in there, but you have also flow on the surrounding on the rock. So you have exchange between the rock flow and the fracture flow. So you have to design somehow nice couple. You have to couple the 2D and the 3D. So the coupling condition is really important, and how to derive them as well. And as you can imagine, in the subsurface, and especially if you're dealing with real application, then you have a lot of physical, chemical phenomena happening, and they are all coupled together at different scales. So you can imagine how difficult it is. And today I will, so my coupling is a real challenge here. And today I will focus on flow, and especially not multi-phase, but single-phase flow, because you will see that already single-phase flow in this geometry is already something that is quite challenging. Okay, so let's start with the model. So we have the DSM models. So this is a model we are using. This is a model that was developed by LabCom Factory. Actually, we use their software to simulate the fracture network. And you can see, here's a pointer here. I know it's not working on the. Okay, so I've shown you just an example with 3 fractures. You see, there is this 3 fracture test cases, only 3 fractures, just to give you an idea of what a fracture is represented, how a fracture is represented. It's a lower dimensional object with respect to the rock, right? You have this rock which is 3D, and we use a radius model. So the fractures is considered like surface, here ellipse, and then they are crossing each other, and the way they are crossing, their orientation, position, all of these parameters are derived from statistical law. So it's a statistic model. So here is one realization, for example, and in 2012, we dealt with this less than 7,000 fracture test case, and we did some benchmarking on this test case. While now, Itasca and LabCom Factory gave us these test cases with more than 1 million fractures, 2 million of intersection. And the question was, how we can simulate flow in there? fracture flow coupled with rocks flow. So if you see, like in the fracture post-medium modeling, which means that you take the fracture into account, with this different model for fractures, and you add the 3D, like the rock, then you end up with some choice that you can make. And in our work, we try to be as much as on the top right? We want accuracy of the background medium and accuracy in representation of fractures. So we try in our work to be as possible close to the original fracture post medium that is given. And we build a mesh on this, and a surface mesh and the volume mesh. But I will come to this now, after the typical problem. So the problem we are dealing with in this study, many papers on it are in the literature, but I will recall you the main equations. So in each fracture, you have Darcy type flow and a conservation of mass, continuity equation. These are the equations in each fracture. Okay? Then you have to couple the flow within each fracture. So you have to add intersection condition between the fractures. Typically, continuity of hydraulic head is what we suppose, and conservation of mass at the fracture intersection. So these are the flow within the fractures, right? Then there is a flow in the rock as well, right? And same kind of equations. You have Darcy type flow, conservation of mass, and some boundary condition. And these two flows are coupled. You have a coupling term. How does the coupling term act? The coupling term acts as a source term in the fracture equation. So you have this QMF here that is exactly the flow coming from the rock into the fractures. And an hypothesis we are doing in all of the presentation, all of the work I will show you today is a continuous hydraulic head model. What does it mean? It means that the fractures we are dealing with are conductive, highly conductive by comparison with the rock, surrounding rock. This continuity of pressure is not the case if you have barrier, for example. If you have fractures that is filled with material blocking the flow, then it's not this model that is the right one, right? So imagine conductive fracture. The fractures are preferential flow paths in this simulation. So the first challenge was the mesh generation, because as you can imagine, we have all of these, as you can see, all of these fractures intersect in very intricate ways. So you can have very small angles. And you need also this meshing to be efficient, right? So what we do is we use unstructured mesh generation, and we ask for the user input quality. So for each triangle, it is defined this way, the delta of k. It is 1 if it's an equilateral triangle, and the lower it is, the bad quality it is, right? So then we would like to have a rather good quality meshes. And we cannot go too low, because otherwise the triangle will be almost flat. So it could be a problem for the numerical method afterwards. So we have developed this software, MODFRAC. MODFRAC is a proprietary software. So this one was developed by Inria Gamma, another Inria team, UTT, which is the University of Troyes, and Serena team. And so we developed this software that is capable of meshing this kind of geometry. The way to guarantee this user input minimum quality is to slightly perform automatic corrections to improve the mesh quality and to keep, what we wanted to do is to keep the original fracture networks, which is the most challenging part. So we did that, and once this mesh is done on the 2D, so you measure fractures, and then you want to perform this volumic mesh based on this 2D mesh. So for this volumic mesh, we use a black box mesh generator from Inria as well, Inria Gamma. And so you have to, just to mention that the surface mesh must be of sufficient good quality to be able to perform the 3D mesh. Because MODFRAC only see the 2D, right? GHS will have to deal with very close fractures that are very close together. So you have to, yeah, it's not because you can have a 2D image that you will have easily the 3D, right? Just to mention this. Regarding the computational time, so MODFRAC is in parallel, multi-threaded code. And then, for example, to mesh a network with 174,000 fractures with 30 million of tetrahedral elements, it takes less than 20 minutes, which is correct, right? You have the mesh and you can do simulations. It's okay. And we check the quality. And of course, the quality is a little bit less than for the 2D because we have not so much control on it. We just, the input is the 2D image and we run the volume measure and then we check the quality. So it's rather good quality, but we have some elements of low quality in our mesh. And this is important to keep in mind. And you will see why after in the solver part, you will see why it's important to keep in mind that we have low quality elements in our mesh and there is no other option to keep them, right? If they're there and we have to deal with them. So the challenge too is to perform large scale simulation that guarantee local mass conservation. So to do that, we used mixed hybrid finite element method. So this method works on simplices. You can work on triangle, tetrahedral element. And the very nice thing with this method is it is locally and globally conservative. So you have this local mass conservation that we really want, especially if you want to do transport afterwards. So what are the unknown? The unknown are on the element, you have the traces of the hydraulic head. So for example, I don't have to. So on each face, you have an unknown, and for triangle, it means on each edge, you have unknowns, which are the hydraulic head. Inside the element, you have the mean head. So inside the tetrahedral element and inside the triangles. And you also have the fluxes through each faces. And of course, we kept this continuity of the pressure at the interface between the rock and the fracture, which means basically that if you take the transfer pressure of a tetrahedral element, it's equal to the mean pressure inside the triangle fractures. So then with that, the very nice feature with this kind of hybridized method is that you can perform static condensation. And then you obtain a Schur complement, which has very nice property. It's symmetric positive definite. So then it's very convenient because you can use your favorite solver to perform the solving of this huge linear system. So you can use direct solver, for example, but you will see, if you use direct solver, you're kind of stuck to small network, right? If you can rather use iterative solver, the RAM consumption will be lower, but then let's see afterwards how it behaves on this kind of problem. So the linear system, basically, you have the unknown, which are only trace of pressure unknowns. So trace of pressure on the tetrahedral element, and we keep them to the mean pressure inside the fractures. Once you have solved this linear system, you can recompute locally, element by element, the fluxes, and therefore the velocity using the basis function. So this is a very convenient method, very nice. And let's see now how it applies to our problem. So we have developed, it's a MATLAB software, NetFM, for prototyping, for testing the method, right? So we have implemented this mixed hybrid finite element for porous fracture flow. And we wanted to test our implementation. So in the literature, there is a benchmark from Inga and co-authors, which provide a test case with 52 fractures, and you can perform flow, porous, and in the fracture, coupled flow. We have a transmissivity of 100 in the fracture network, so each fracture has the same transmissivity, and the permeability in the rock is equal to 1. So you see that these highly conductive fractures, permeability of the fractures, transmissivity is much higher than the one of the rock matrix. So no problem to solve with a direct solver on these test cases. 19 seconds, perfect, very small test case. So it's okay. Here is the results that we obtained. And in this paper, they perform code comparison So they have this spread, all these curves. And so we tested our code. So our result is in this orange curve. So it's just, you just plot the pressure along your diagonal of your domain. And then we end up with something that is really in agreement with what others obtain. Okay, so now we wanted to say, okay, we have a code, we have a mixed hybrid finite element method, we have everything. Now let's go for larger test cases because we have them. We have the mesh now, so we can perform larger test cases. So let's go with the test case that the LabCom factory gave us. So this one is called L20. L20 is because the cube is of size 20, right? And you have less than 2,000 fractures in there. So let's go for a direct solver. Okay, for these test cases, you have less than 2 million of cells, tetrahedral elements, 27 gigabytes of RAM. Okay, let's try higher now. L60, cube of size 60, 40,000 fractures. Yeah, you see the RAM consumption with the direct solver. So let's key here. More than 100 gigabytes start to become large, and then it will be higher and higher if you increase the test cases. So direct solvers are efficient, but the RAM consumption is very high. So we want to say, okay, let's go for an iterative solver. We have very nice symmetric positive definite system. Let's go for conjugate gradients. Okay. But you have to precondition because your problem is hill condition. So then you see that incomplete Cholesky is not an option. It's not efficient in this case. We tried a multi-grid preconditioner, AMGCL. And you see that with this solver, the number of iterations can reach 5,000 iterations only for this L60, so 40,000 fractures, and it takes 4 hours, right? Remember, at the beginning, I say, I want to have a simulation that takes not too much time to run, right? I want to perform Monte Carlo simulation. I want to run several realizations of my fracture network and doing flow simulation in there. And this one starts to be quite a large number of iterations and takes quite some time, right? And we imagine it would be worse if we increase the test cases, right? So, but the RAM consumption is fine. I'm happy. I just changed the RAM consumption is okay, but the number of iterations starts to increase a lot and the computational time as well. But still, it's working, which is already a step, right? It's working. So let's analyze a little bit further. So about the geometrical complexity impact. So what are the, so now I added test cases. So you see that the number of fractures increase, it's an NF. So you go until 90,000 fractures in the L80 test cases, okay? So here are the convergence curves. And you see that as the test case becomes more complex, you have these curves going to the right, which means larger number of iterations. Okay, but it can converge, which is already something, right? And but it takes some days, right? For example, for the L80 simulation, more than 2 days. It's taking some time. So yeah, so maybe it's not the option that we will keep, right? We will try to, because it's really dependent on the test case. Huh? Remember, it's really dependent on the test case and why it's so bad. I just want to try to explain you the importance of the mesh quality. So we have a bad mesh. We have a mesh, and this mesh has some low quality elements inside, right? And we have to deal with them. It's there. So let's see how it impacts the simulation. So here I will show you a bunch of simulations, a set of simulations that emphasize this phenomenon. So the importance, why this mesh has so influence on the iterative solver. So here, if you consider only throwing the fractures, it's the first line, GFN mesh 2D. Okay. Now, these two simulations here, FPM is fracture force media flow, FPM is for porous media only. You will see afterwards while I put these two, because the mesh is the same, right? We keep the same mesh, except that in one FPM 100, sorry, you have this mesh quality, which is 10 to the power minus 6. And same with so the third line here, you take the mesh that is constrained by the fractures, and you only simulate porous flow. No coupling, only porous flow. And then I take a mesh with tetrahedral elements in a cube. So the mesh quality is very nice, 0.3, perfect. Okay, now let's see how the solver deals with that. So if you take this DFN flow only flow in the fractures, 3,000 iterations, okay? Now let's see if you perform fracture porous media simulation. Now it's the same simulation I've shown you before, 5,000 iterations, 4 hours, right? Now let's imagine I do not solve the coupling. I only solve porous flow. Okay, the fracture are just here to constrain the mesh, but there is no coupling. I just simulate flow in this mesh, right? You see the number of iterations? Almost the same, 5,000. Then, if I solve the same problem on a very nice mesh, 69 iterations. So you see the difference between only the mesh. The same simulation. Flow simulation, only the mesh differs. One is coming for the fractures constraint, and the other one is a very nice tetrahedral mesh. So you see that the mesh has a very strong impact. And there are some recent works about that, about how multigrid is impacted by regions with low quality cell elements. Regarding the heterogeneous properties, so in what I've shown you, the rock was 1, permeability of 1, and the fracture 100, right? So now let's try to see if we take a permeability that change from one fracture to another, right? And you have a range that could be of 7 orders of magnitude. So it's quite large. So you have a problem with very different heterogeneous properties. And the rock, or the permeability of the rock, is taken 10 to the power minus 8 in that case. And you see that compared to this, the first line is you take 1, permeability of 1 in the rock, 100 in the fractures. You can solve it. It's a problem we have seen. It's okay. But if we take these heterogeneous test cases with a range of permeability in the fracture, which is 7 orders of magnitude, it means that you have fractures that have 10 to the minus 6, and you can have fractures with a transmissivity of 20, maybe. So you have this very large range of transmissivity inside the fracture network, and you see that you cannot solve it with MGCL as preconditional. It's not working anymore. And the convergence curve shows you that, right? If you increase the heterogeneity contrast between the rock and the fracture, then you end up with a simulation that takes forever, right? So then we switch to another preconditional, which is in the class of HPDDM, High Performance Unified Framework for Domain Decomposition Methods. So here you have all the references that the researchers that have developed this library and this method. And so it is integrated in PETSI, which is very nice to use, because then once you have plugged into PETSI, then you have all of these methods available to you. So it's very convenient for testing different solvers. It's open source, it's used in academia industry, it's written in C++, you have interfaces, and you can run on supercomputers as well. So here just to give a clue, so how it works, you have to partition the domain, and a way to partition the domain, for example, is to partition a mesh, right? You can use a mesh, and you use your favorite mesh partitioner. It could be Scotch, it could be Metis, and then here is an example with Metis, and then you have a partition of your domain based on your mesh. In this work, we have tried this HPDDM GNEO framework. So what is it? It's a two-level domain decomposition method based on a spectral cross grid. So the final level is additive Schwarz, or you can have restricted additive Schwarz, so ASM or RAS method. The only difference is that the RAS leads to asymmetry. So you have to use GMRES instead of PCG. So this is the only difference between the two. And there is another difference, is that RAS is more efficient. That's why we use it, actually. And the coarse level, so you have this fine level. So really the preconditioner is made of two, so the fine level and the coarse level. And the coarse level is based on the GENEO framework, and it's based on the resolution of the generalized eigenvalue problem. So this method, so that has been developed in the paper that you cannot read it, but I can give you the reference later. These methods require two things: a partition of the mesh, and in our case, remember, we have this 2D mesh coupled to a 3D mesh, right? So you have the two. So we have to somehow partition our domain, and this partition must have an overlap. So if you use Metis, then you will have a partition, but with no overlap. We will have just one domain. So you take the mesh, the tetrahedral mesh, for example, you partition using Metis, and then what we do in our code, we add one layer of overlap. But the layer of overlap should be in the rock, but you have to do the overlap in the fracture mesh as well. So this is what you can see. On the line on the top, you have in blue and green and orange, you have the different mesh, and the red is the overlap, right, between the different subdomains. In the fractures, same, except that the pink are the triangles that are on the overlap. So you need this, you need to build it. Why you need to build this partition? Because GENEO requires the so-called Neumann matrices. What are these matrices? It's just an assembly. So you have your problem, right? You assemble on this meshed with one layer overlap, and it gives you the Neumann matrices. And you have to, of course, to give some local global mapping from the local domain to the subdomain. And once you do that, once you have done that, so these have been adapted to fracture networks by doing this partition of the domain with overlap for the pores and for the fractures. Once you have this, we can test, right? So we come back. We come back to this test cases that is here, and that took 4 hours and 5,000 iterations with AMGCL as preconditioner. Now, if we use GENEO, then it's much better. You have 57 iterations, and you use 522 MPI processes. So this means, so I have to mention that one MPI process equals one subdomain. So the number of subdomains gives the number of MPI processes you are using. So you see that it takes only 52 seconds, 57 iterations. So let's go further. The test case we are not able to solve, a heterogeneous test case. We are not able to solve in reasonable time with MGCL as preconditioner. Now we can perform it actually. It takes 67 iterations. So this is the difference, huh? Really, the number of iterations really decreased. It's really convenient. And it works pretty fast. And you can see the convergence curve. Huh? It's really working very efficiently. So now let's go for larger test cases. So we have tested on this L60. So now let's increase the complexity of our fracture network. So we increase the number of fractures. So as you can see, for example, the biggest one that we have tested so far has about less than 700,000 fractures, right? And the number of dots is 242 million of dots. So it starts to be very huge test cases, and we wanted to test the performance of HPDDM in that case. So remember, there is no other competition because the other one cannot deal with this big network, right? And here are the results. So I only plug the L130 and 160 because they are the largest one, but you can see that the computational time remained really reasonable, 5 minutes, something, and 51 iterations. And it was run with this biggest one, was run on 6,825 MPI processes, equals number of subdomains, right? So, and you see that we have tested homogeneous case, 1 versus 100, heterogeneous case. Do not see much difference, right? It's working in both cases. It's like very super efficient. And here is just to show you the convergence curve for different test cases. If you change the test cases, if you increase the number of fractures, if you increase the heterogeneity, it's super robust. Same heterogeneous case. So really, it has proven that for this application, so far it's the best I know that can. Time remains reasonable, saying open the door to Monte Carlo simulation if you want, right? So how much time do I have? It's okay? Okay. I just want to mention some work we are also doing to try to reduce the number of dots. Remember, I meshed with triangles and tetrahedral elements. But when you have these very dense fracture networks and your mesh respects the intersection between the fractures. So you cannot coarsen them as much as you want. If you take a coarse mesh step, you will end up with the same number of cells because it cannot be much better than with triangles. So the idea is to use hybrid high order method, HHO. That remember, this HHO it can deal with any shape, like polytopes, which is super convenient because if you, for example, imagine you agglomerate with triangles, you can have much less cells than with triangles, right? You can have these polytopal elements and you can deal with them. So here is an example with 3 cells, and you have the unknowns. So you can choose the degree L and K depending on what you want on the cell face or inside. And so basically, just it's the same, the unknowns are the same place as the mixed hybrids. So this is very convenient to go from one method to the other because this one is more general, it works on polytopes, but it's working with unknowns that are located in the same place, right? And you can do static condensation as well. So you have seen that these inner unknowns disappear with static condensation. You end up with a symmetric positive decision system. So very nice. So this is something that we are working on. We want to do that to reduce the computational time. So the first step in that direction was this, in this paper, was to, okay, my mesh generator is capable of so meshing the fracture network, and I can choose a mesh step that could be different from one fracture to another. So how I choose? In fracture flow, the flow is highly channeled, which means that only some fractures may carry most of the flow. So you can imagine, okay, let's mesh finely these fractures that carry most of the flow, and we do a coarse mesh in the other one, right? But then we end up with some non-matching grids. You can see here, it's very clear. There is a blue and orange. You can see that the mesh are really not matching. You have a fine mesh at the intersection. You have a very coarse mesh on the other side. And it's okay, it's not matching. But you can add vertices. So that's what we have done. We can add vertices to make the mesh conform, right? So this will be a triangle. This is a small picture I've drawn here. You have these 3 initial dots, which are the vertices of the triangles. And then to make the mesh conform, you add some extra dots, which create some kind of polygons, shape of triangles, but more vertices, right? And then what happens? We can do that, right? You just have to first know which fracture carry most of the flow. So you can do this with different ways. You can use graph, for example, to just have an idea of which fractures matter the most. Or you can do a coarse simulation beforehand. That's what we did in this paper. So there are different options. And it allows to reduce the number of unknowns, because then all these fractures that are coarsened because they do not take much part of the flow, then you can save. Basically, on these test cases, we saved it was a 500,000 fracture test cases with 10 million of triangles. Here was only 2D. I'm sorry, I'm not sure I mentioned it, but it's only 2D. Then you save 15% of the total time, 12% of the RAM compared to a fine mesh simulation. If you have meshed in a conform way and every fracture has the same mesh. But you see that, as I said at the beginning, it's not easy to coarsen with, as you have the intersection as constraint in your 2D mesh. Not easy. So we want to, so what I'm doing now, I'm working on it with, especially with Down and Down in my team, to be able to agglomerate the triangles to build polytopal cells And with this polytopic cells, you can imagine that we save a lot of computational DOF. We reduce them a lot. Okay, this is my conclusion. So, we have successfully meshed fractures with 700,000 fractures, and it ended up with quite a lot of tetrahedral elements, more than 100 million. And so this, having this mesh, having these large test cases, we were able to design some kind of methodology to test different solvers, especially that we have FETSI now. We can really have various, attend various solvers. So this is the beginning of the story, I can tell. Maybe we can test other solvers as well. We have excellent results with the HPD MGNO framework. And this works very well, and it works independently on the complexity of the test cases, the fracture numbers, and also with respect to the heterogeneity, which is very nice. As I mentioned a little bit in the end, we are using now, we want to use polytopic methods much more to reduce the number of DOF, because then the more we can decrease the number of DOFs, the more efficient we can be later. So we have so far performed simulation with HHO, so the paper I mentioned. And this one exploits the challenging effect of the DFN. It means you match finally only where it matters. As a perspective, we would like to add more general fracture models. Like we have not tested simulation with wells. I can include wells in the mesh, but I have not performed simulation with wells so far. We'd like to include that fractures are coming from the data actually, and non-planar fractures. Maybe to consider as well geological and geomechanic ground fracture networks. I mentioned here the work of Adriana Palese from Imperial College. And also we have a methodology to test solvers, so why not testing other solvers as well? So the solver developed in my team from Martin Voralik based on a posteriori error estimate for multi-grid solvers. A work I started with Ludmil Dikatanov on subspace correction methods. Although multi-grid, as I said, I'm using MGCL because it's kind of a black box. I could use it directly. But in the literature, it's mentioned that multi-grid is not well suited for hybridized version because the subspace are not easily embedded in one another. So maybe there are some implementations that would be more robust with respect to hybridized methods. So that's a direction we'd like to explore more in the future. The software, so here we have this fully parallel solver part, but in what is nice with this hybrid method is that you can do a lot of things in parallel, basically everything in parallel. So for now, my MATLAB code is doing, or MATLAB code is doing most of the job, but we would like to put more in the C++ part, and then to build the local matrices in parallel, to assemble in parallel, and to do the post-processing in parallel. So a lot of things have to be developed, but it's a way to have very, very efficient software. Polytopic methods. So as I said, we would like to do some mesh agglomeration, refinement only where it matters. And we are starting to work on this using a posteriori error estimate, which would guide us to refine and to coarsen where it's needed. And although also I would really much like to work on this upscaling reduced models, because as I said, this fine scale simulation takes quite a lot of resources. I run it on supercomputers, right? So why not learning from this fine scale simulation to design reduced models? And I mentioned the work of Marcel Murad from LNCC, and I hope, yeah, maybe in the future we can work together. And that's it. Thank you for your attention.
We have, okay. Hello. Astrid, do we have any questions online? No? Okay. And in the room?
Thank you for your talk. First, I had one first question about when you're saying the percentage in like the final solver, how much time does it take to mesh, to assembly the matrix, and to solve the problem? Can you comment on that?
Alors, so I focus on the solver part because it was the most consuming time, right? Especially in 3D, it takes hours with the MJCLS preconditioner. So really, it was the most consuming part. Regarding the mesh, as I said, in the test case I've shown, the mesh generation can take, for the 3D with a very, very large, it can take, I think the last one takes more than 2 days to mesh because it's really huge. But it's not parallel, this one. And it's not mine, but maybe there are hope to have a parallel version. But for the, but once you have the mesh, right, you have done it, then you do it once, right? After you can run as much simulation you want with that, right? For the assembly part, so I use vectorization in MATLAB a lot. So it speeds up the computation. But of course, I would like to do it like in C++ version, like in fully parallel. I would like to use PETSI for assembly, actually, because it will be, PETSI cannot be, it's really very efficient. And for the post-processing, same. You have to have, it's on each element. You can recompute locally the fluxes and the mean pressure. So it's really independent from one cell to another. So basically, it's embarrassingly parallel. You have to just it's completely independent. So that's also very nice. But yeah, I have not, you see, I put effort in some parts and then I need some more effort in other parts to be fair, right? To have, try to.
Okay. And another question, at the beginning, you are showing that this AMG is like multi-grid, it's algebraic multi-grid preconditioning. And in this case, it sounds that it's very, there is a strong dependence on the number of fractures. And then you get to this domain decomposition preconditioner, and it's working and scanning very well. And I'm not sure I understand, like maybe theoretically, why it's working so well with domain decomposition and why it's not working on algebraic multi-grid.
Actually, this HPDDM framework with Geneo, it's a two-level preconditioners, and that's the strength of two-level preconditioners that are scalable, actually. So we have performed some, I think I have them somewhere, but we have performed, I can show you later if you want. We have performed weak scalability and strong scalability with HPDDM Geneo, and it works perfectly fine. What I mean by that is that the number of iteration is independent of the size of your of the number of subdomains you take, right? So that is the strength of two-level domain decomposition methods. And we were hoping that we could check this feature in our problem, and it works. It works. So we have weak scalability, strong scalability with this two-level domain decomposition. Yeah.
And are there like theoretical guarantees that it's going to be stable?
Yeah.
Okay.
There are theorems you have there is a book from Frédéric Natta, Victorita Dolean you can have, and there is a theorem inside guaranteeing that this is the case, right? So so it's very strong theoretically. So then, and we could check it works in practice for this large scale application. Yeah.
Thank you.
You're welcome. Thank you. I will. So the question is, thanks for the talk. This mesh generation method on fractures could be used in solving Navier-Stokes with obstacles to improve their performance at coastal level. Yeah, I've never done that, but I have constraints in my. So this mesh generator is really designed for fractures in terms that it computes the intersection between the different fractures. And then it is used later on to build the mesh independently from one fracture to another. That's why that's where the parallel is taken into place, right, in this 2D measure. So maybe, I don't know, maybe it could be, because on the surface plane, we have a lot of constraints. All these intersections are constraints for the 2D mesh, right? So maybe, I don't know, we could try something. Thanks for the question.
Thanks. Any other online? No more questions? Anyone in the room? No? I have let's say a little question, more like an interest. Uh, how well does this approach scale when you increase the different dimensions of like, is it an exponential, let's say algorithmically, not in terms of algorithmically. So it is exponential with the size of your mesh. It is linear. The time complexity of computing your meshes and all of that. As you increase dimension,
So you mean
a bigger, let's say, a bigger problem, how much additionally it costs? It is the time, let's put it like this, the time to compute increases linearly as you increase the dimension, or increases exponentially?
you mean about the mesh? Or I think it depends on the parts of the you are looking at, actually. Because there are some parts that are like embarrassingly parallel. So then the more effort you put, then the better it's all. Regarding the mesh, yeah, it's I have not tested fully the how evolves the time with respect to the different test cases. I could do that, yes, to have an idea. But same, the 2D measure could be run on different cores. So then the more you put effort on it, then the more the less it takes time. So
Yeah.
and yeah, and for the solver part, it's super robust. So
Yeah, no, I mean, it's true that in your case, as you have this fracture, the complexity is also attached to the time complexity, algorithmic complexity is attached to the particular setting, no, as you were saying.
and it's really linked to the geometry that I have at the beginning, because if I have very dense network with a lot of constraints, then it impacts the number of low quality elements I have, and then it impacts the convergence. I don't know if you remember this 69 iteration on a very nice tetrahedral mesh for the flow only, porous flow, and then you take this really bad quality mesh, and then you end up with a computational time that really increase a lot. So yeah.
Awesome. Then I have I'm sorry because this is very interesting, and you know let's say we are near these problems. How this is like a more general question, no? How do you validate that the model is accurate with what is happening in nature? I mean, not you in particular. How you guys do it, no? It's like you have like probes that validate that the model is correct.
Yeah, that's part of the community to set benchmark on this, right? And I know that a group in Bergen are doing experiments on the fine scale level just to see if the models are correct. And I think it's not that easy to validate, and that's why most of the time we do code comparison to be sure that we obtain the same. But that's true that about the modeling, I think the hypothesis we're making, could be like, for example, the continuity of pressure. I mean, you have barriers, then you have to change the model, right? You have to redo everything. No, you have to the condition change. It's just the discontinuity of pressure at the fracture. That's true that validation is something that is quite huge to perform, actually, and to be confident in what we obtain, because there are so many uncertainties that, yeah. That's a very the question is very wide area to explore. I mean,
it's not a criticism or anything; it's just a curiosity, because I understand that at the end, I mean, it's a very complex process that is also very hard to observe, no?
And it's hard to measure as well. And,
even I guess that creating, or let's say, finding the different fractures is also another problem, I guess, no? For geology.
I mean, I have shown a model which is it is a statistical one, but in practice, the resolution of the device are not that small. That scale is not that small, right? You cannot see the small fractures with tools that image the subsurface, right? So far, so yeah, that's why we build a statistical model, because we don't have the data. But yeah, all of these are to be calibrated. So I'm not an expert on this. I mean, that's why I work with hydrogeologists and in the oceans in particular. And the idea is really to try to incorporate this. That's why I think the direction that I would like to explore is to add this more natural fracture network that we can see on the field to these models to have a picture which is more realistic. And yeah, and remember this big the site where I put all the couplings. And yeah, I think we have worked for years now.
Yeah, no, I mean, it's, now that you mention it, let's say, in a probably completely different domain, you know, this image generation using AI that you type something and generates a very nice looking image and all of that. Actually, they use partial differential equations in that process because they have a way of, let's say, redrawing the image. It's called stable diffusion. So they add like some features that you expect to have in an image. So they look nice and let's say the drawings or the curves are follow a certain pattern and all of that. And they work trying to, they start with a, let's say, bad image and progressively improve it. And so I think that this idea could be extended to many different domains, no? Of this progressive redrawing, let's say, or like correction using some domain knowledge that you know that, I mean, a fracture cannot go like this, that has to be smooth or something like that. And it has been a revolution there because the cost is really low, no? That is why we now see it everywhere. Awesome. Any more questions? Yeah. Well, I think actually we are a little bit out of time. So thank you very much. And thank you, everybody participating online. Thanks. Bye.